Here's a simple idealized picture or model of a wave. The line represents the water surface of a wave. We can freeze the wave or take a snapshot of it. This is a crest, a trough. The difference in height between crest and trough divided by 2 is the amplitude of the wave, denoted by a capital A. The wavelength is the distance from crest to crest, or between trough to trough, and it's almost always denoted by the Greek letter lambda. This snapshot is also a graph of the displacement or position of the surface as a function of distance. The displacement of the crest is the maximum in the surface displacement. The displacement of the trough is the minimum in the surface displacement of the wave. We can unfreeze the wave and watch it in time. You see that any given crest or trough moves or travels in one direction. Let's identify a point or molecule on the wave's surface by a red dot. It will not move with the crest. Instead, it bobs up and down, perpendicular to the direction of motion of the crests. Half of the displacement of the molecule is the amplitude of the wave. In this idealized model, the matter, that is the points or molecules, move up and down and not in the direction of the waves. We can pick any molecule on the surface of the wave, and we will see that it moves up and down, and the distance that it moves is twice the amplitude. The molecules making up the medium, or let's just say the medium itself, moves perpendicular or transverse to the wave's motion. For this reason, we call this wave a transverse wave. Let's focus upon the transverse motion of the medium. The medium which the wave passes through is going up and down in time, and we can trace out its motion in a plot of displacement versus time. This looks a lot like the curve in a displacement versus distance plot. We can still identify the amplitude. It's half the total up and down displacement that the particle or molecule undergoes. And the time that it takes for a molecule to complete one full cycle, that is starting from crest, descending to the trough, and ascending to a crest, is called the period of the wave. It is the time between crests in a displacement versus time plot. Here's a static wave frozen in time. Let's unfreeze it and see what it looks like if it has a long period. Let's freeze it again and restart it with a shorter period. As you can see, a wave of given wavelength and amplitude can have different periods. The wave with a shorter period appears to travel more quickly. A wave with a longer period moves more slowly. Now, we often denote period with a capital T. The frequency of the wave is the number of crests that pass by in a time interval. So you can use a timer and count the number of crests that pass by. We start at 0 and count crests, 1, 2, 3, in a time of 6.6 seconds. That is, 3 cycles have passed in 6.6 seconds, or the frequency is 3 on 6.6, or 0.45 cycles per second. Or if I use the time to count only one crest passing by, that's 1 cycle per 2.2 seconds. This is the same as 1 on the period of the wave. Frequency is often denoted with a small f, and the mathematical relationship between frequency and period is this. Again, the frequency of the wave is 1 on the period of the wave. By the way, frequency has units of inverse seconds. As the number of cycles is just a number, it doesn't have units of mass, length, or time, or a combination of these. So the frequency is expressed as 0.45 inverse seconds. Now, an inverse second is equivalent to another unit, a hertz, abbreviated by capital HZ. Hertz was a German physicist who made important discoveries about electromagnetic radiation, that is, radio waves, microwaves, light. Electromagnetic radiation is described with the same characteristics of a wave, wavelength and frequency. But radiation is also very different from these water waves. More on that later. So if we talk about a wave of, say, 333 hertz, we know that one cycle of the wave passes in 3,000th of a second, or that its period is 3,000th of a second. But we don't know its wavelength or amplitude. All of these waves have the same frequency, but they have different wavelengths and amplitudes.